Hi, hello everyone. Here we are going to discuss about GATE 2024 electrical engineering questions from the subject electrical machines. We have got around 5 questions from the electrical machines, and the questions are like this. The question is asked from induction machines. This question. He has given that a three-phase 50 Hz 6-pole induction motor runs at 960 RPM. The stator copper losses, core losses, and the rotational losses of the motor can be neglected. The percentage efficiency of the motor is asking. So motor efficiency, how do you write? The percentage efficiency of the motor will be motor output divided by motor input. Motor output divided by motor input. He said that the stator copper losses and core losses are neglected. Okay. If stator copper losses and core losses are neglected, you see this is the power flow diagram of the induction machine. If these losses, stator core loss and copper loss are neglected, then I can say that rotor input is nothing but motor input. And one more thing also he mentioned in the question, that is rotational losses of the motor can be neglected. So that is mechanical losses also can be neglected. If this is neglected, then I can say the motor output is nothing but gross mechanical power. So now here in the efficiency formula, I can replace, instead of PMO, that is motor output, I can write PGM. And instead of motor input, I can write rotor input. Okay. So we do not have any information about the rating of the induction machine, and nothing, or voltage rating, something, current rating, nothing is there, power rating, nothing is there. So only thing is he has just given 50 Hz frequency, 6 pole, and 960 RPM. So the rotor speed he has given. So if you remember the formula, the power flow in the induction machine. If you remember, the rotor input is to rotor copper losses is to gross mechanical power is actually 1 is to S is to 1 minus S. Now we want a ratio between gross mechanical power and rotor input. So the gross mechanical power to the rotor input is taken as this one, this relation. So 1 minus S into PRI divided by 1, or 1 minus S sigma. So that means here 1 minus S you need to calculate. If you can calculate the slip, then that could be the answer. How will you calculate the slip? Slip in the induction motor will be Ns minus Nr divided by Ns. Ns, how do you calculate Ns? Synchronous speed, 120 into 50. 50 Hz frequency divided by 6 poles. So you'll get 1000 RPM. So 1000 RPM minus rotor speed is 960 RPM divided by 1000. You'll get 40 divided by 1000. You'll get 400. 4 divided by 100, maybe 4% you can take. So if the slip is 4%, 1 minus 0.04 will be 0.96. This means 96% is the efficiency of the rotor. So here rotor efficiency and motor efficiency both are same. Rotor efficiency and motor efficiency both are same because losses are neglected. So C is the answer. This is one mark question. And if you see this one, this question is from transformer. Which one of the following options represents possible voltage polarities in a single phase 2-winding transformer? Here Vp is the applied primary voltage and Ep is the induced primary voltage. Vs is the open circuit secondary voltage and Es is the induced secondary voltage. So E's are induced voltages and V's are applied voltage and secondary voltage. Of course, Vp is applied voltage and Vs is secondary voltage. So as it is a transformer, the transformer he's saying that primary and secondary. So no doubt the source is connected here. No doubt the source is connected here. If it is secondary, so no doubt the load is connected here. Okay. Remember, if you want to know the polarities, KVL and Lenz law must be satisfied. If I to satisfy KVL, let us take up it as 100 volts here. So what will be the EP? Approximately 100. So EP is also going to be approximately 100 because I am not taking any losses here. So EP is also 100. So if you write KVL, it will be plus 100 minus 100 is equal to 0 in this primary loop. So KVL is satisfied here. You check with other options also. If you check with other option, you will get EP. So whatever the applied voltage if I am applying 100, so EP must be 100. So if I write KVL plus 100 plus 100 is equal to 0. So this is not satisfying KVL. So C is not going to be the correct answer. Similarly, you look at D. Okay, if I supply 100 volts, so plus 100 plus 100 because EP is also 100 now. So leaving polarity I'm considering plus 100 plus 100 is equal to 0. So 200 is not equal to 0, right? So D option is also not satisfying. So A option is satisfying and let us check with the B option. Let us check with the B option. So minus 100 plus 100 minus 100 plus 100 is equal to 0. So this is satisfying. So A and B options are satisfying and C and D options are not satisfying. So I can eliminate 2. So now out of this A, B, now you need to check with the secondary side also. So let us assume he did not mention any turns ratio. So let us assume secondary voltage is also 100. Okay, I'm just assuming. So Vs is also 100. So plus 100 minus 100 is equal to 0. So this KVL is satisfied. KVL means the sum of the voltages in a loop equal to 0. Okay. Similarly here also if you connect 100 and 100, so plus 100 minus 100 is equal to 0. So both on the primary side and secondary side the KVLs are satisfied. Now you need to check Lenz law because he has given as a transformer. He has given it as a transformer. So you need to check the Lenz law. So if you check the Lenz law, so let me erase this. Let me erase this. In the first option, I am connecting a source like this with positive polarity, of course, alternating voltage source. Now this alternating voltage source is going to drive a current, and that current is flowing through this winding in this direction. According to this current direction, the flux produced by this current carrying conductor will be upward. Now this flux is going to create an EMF in the first coil and also going to create an EMF in the second coil. Okay. Now the EMF is going to oppose the very cause of its production. The cause for the production of induced EMF here is due to what? Is due to flux. Now to oppose the flux lines, if I have a load, let me take up a load. If I have a load, now to oppose this flux line, the secondary induced EMF has to drive a current and it has to produce a flux in quite opposite to the primary flux. To produce a flux in the upward direction, the secondary induced EMF has to drive a current in this way. That means what? The current has to leave from the dot terminal. Then only you can get the flux in the upward direction. So this is what I can say. This coupling, I can say, this coupling is a magnetic coupling, which is negative coupling. This is negative magnetic coupling. Transformer is a negative magnetic coupled circuit. It is not positive coupling, maybe not additive coupling. This is subtraction. The flux produced in the secondary is going to oppose the flux produced in the primary. The MMF produced at the secondary must be compensated by the MMF produced at the primary. So MMF balance has to be happen. They should not add, they should oppose. So negative coupled circuit. Transformer is a negative coupled circuit. So A is satisfied. Let us check with the B. Let us check with the B. So the polarities he has given it as positive, negative, alternating voltage source. Now from the positive polarity the current leaves. So if the current enters here, now the current flowing in the turns will be in this direction. Quite opposite to the option A current direction. Now if the current direction is like this, if you apply thumb rule, then the flux produced by this current carrying conductor will be downward. So this is my phi 1. Now phi 1 is going to link with a coil 2 turns and induces an EMF. That induces the EMF is going to that EMF is going to drive the current through the load. Okay, this EMF has to drive the current of the load. He mentioned that the polarities of the voltage at the load is positive here. Positive here. That means the current is leaving here now. Secondary is acting like a source now because it is going to deliver the current to the load. So if the current in the winding is in this direction, then the flux produced by the secondary winding is going to be in this direction. So phi 2 is not opposing phi 1. So it is positive coupling. It is positive coupling. The option B is positive coupling. Okay. So transformer is a negative coupled device. So option A will be the better suitable option. Correct answer compared to option B. Because magnetomotive force balance has to be happen. Okay. Right. So negative coupled circuit. Negative coupled circuit is the correct answer. Okay. So be careful. How can you say that the current direction is in this direction? Yeah. According to positive polarity only, we are taking the positive. The induced EMF in the secondary winding is going to deliver the current because this winding is acting like a source to the load now, to this load. So it is going to deliver, the ES is going to deliver the current from the positive terminal. So if the current is delivered from the positive terminal, then the flux produced is going to be, definitely upward direction, which is aiding with the fiber. So it is a positive coupling. Okay. So option A is the correct answer. And the other way is also there, that is sense of the winding. If you look at the sense of the winding, this winding is wounded from the top of the core and ended at bottom of the core. Similarly, this winding is also wounded from top of the core and ended at the bottom of the core. Okay. You see the dot is given at bottom turn of the bottom turn, or otherwise the winding which is ended at the bottom turn. Okay. Okay. Now here top turn. So which represents here the current is leaving and here the current is leaving. Current is leaving from bottom turn and the current is leaving from top turn. So definitely it's a negative coupling. And you see here the current is entering at bottom terminal, and current is leaving at top terminal. Current is entering at if current entering at bottom terminal, so current should leave at bottom terminal. Then only you can say negative coupling. Otherwise, no. Okay. Dots can be taken in any manner. Okay. So right. So better you go ahead with just KVL and coupling. Negative coupling or positive coupling. So select the negative coupled devices. A is the better correct answer. And coming to this question, of course, this is a previous one. This one is 1 mark question. And the next one. A three-phase 11 kV 10 MVA synchronous generator is connected to an inductive load of power factor via a lossless line with per phase inductive reactance of 5 ohms. The per phase synchronous reactance of the generator is 30 ohms with a negligible armature resistance. If the generator is producing the rated current at the rated voltage, then the power factor at the terminal of the generator is. So if you see the diagram according to the question I have taken, So this is the generator. He is asking the power factor at the terminals of the generator. So you need to find out from here. If you see from the generator, what will be the power factor? So this generator is connected to the load. This generator is connected to the load of 0.866 lagging power factor through a line, lossless line, because we do not have a resistance. This load power factor is already given 0.866. Okay, it has some, he's saying that inductive load means resistance and inductor will be there. So cos inverse of 0.86 you will get phi is equal to 30 degrees. Okay, right. Now for this resistance nature and reactance nature, the impedance angle is 30 degrees. The load power factor, this load power factor is 0.866. but we don't want the power factor from at the we don't want the power factor at the terminals of the load. We want the power factor from the generator terminals. Now here I can say the generator can see the generator can see let me show you. This generator can see, it is not visible. This generator can see this generator can see load impedance plus line impedance, right? This generator can see load impedance plus line impedance. Only load power factor is 0.86. For that you are adding an extra line reactance. So it is going to be inductive nature still increases. If inductive nature still increases, the power factor will fall. The power factor will fall. Yes or no? So the generator can see more. The generator can see more reactance nature. Can see the impedance as load impedance plus line reactance. Load impedance is RL plus XL, JXL plus line reactance. So the inductive reactance is increasing. If inductive reactance increases, the power factor decreases. So answer should be less than 0.866. So it cannot be 0.87 lagging. It cannot be 0.87 leading. So definitely answer is lagging only. No, it cannot be leading because the inductive nature is adding. So the only best possible option is 0.63 lagging. Okay, right. Now if you see this one, this question is from induction machine. And of course, this question is of 2 marks. And here, a three-phase star-connected slip-ring induction motor has the following parameters referred to stator. So the equivalent circuit, in the equivalent circuit, I can mention all these values. The stator resistance is given as 3 ohms, stator reactance is given as 2 ohms, and stator rotor reactance is given as 2 ohms, and the rotor resistance is given as 2.5. Now he's asking the per phase stator to rotor effective, the per phase stator to rotor effective turns ratio is 3:1. So N1 by N2 ratio he has given it as 3. I can take up N2 by N1 as 1 by 3. This is what I can say transformation ratio. But he has given turns ratio. Transformation ratio. This is turns ratio. Okay. Now he is saying one more thing, that the rotor winding is also star connected. Stator winding is star connected, rotor winding is also star connected. The magnetizing reactance and the core losses of the motor can be neglected. To have the maximum torque at starting, the value of extra resistance in ohms to be connected in series with each phase of the rotor winding. Referred to rotor side is asking, by the way. So the equivalent circuit is referred to stator side. So he is asking what should be the extra resistance to be connected in the rotor, such that you will get maximum torque at starting itself. Maximum torque at starting itself. You know the condition, it is the same like maximum power transfer theorem. The variable resistor must be equal to constant value. So here, which is the variable here? R2 by S is a variable. No? As a speed changes, slip changes. If the slip changes, R2 by S also changes. Okay. So the condition to get maximum torque is, condition for maximum torque is variable must be equal to constant term. So what is the variable term here? R2 dash by S is equal to constant term. Remaining all terms are constant terms. That is stator resistance square plus stator reactance plus rotor reactance. Okay, magnitude I am taking. Now he is asking what is the extra resistance to be connected? What is the extra resistance to be connected to get maximum torquing at starting. At starting, slip is equal to 1. Slip is equal to 1 at starting. So we know all the values. R2 dash is how much? 2.5. Now you need to calculate extra resistance. What is RS square? 3 square. What is XS square? 2. What is XR dash? 2. So 3 square plus 4 square is 25. Root of 25 will be 5. So the extra resistance you are going to get it as 5 minus 2.5. You will get it as 2.5. This is the extra resistance calculated on stator side with respect to stator. But he is asking not on the stator. If you fill with 2.5, 2.5 is a wrong answer. He is asking refer to rotor side. Okay, right. So if you refer the R external referred to the rotor side, refer to rotor, it will be K square times R external, right? K square times R external. What is K? Transformation ratio, N2 by N1. N1 by N2 is given it as 3. N2 by N1 will be 1 by 3 whole square into 2.5. So 2.5 divided by 9. So if you solve this one, 2.5 divided by 9, you will get it as around 0.2727. 0.277 ohms per phase. So in each and every rotor phase, we need to connect the extra resistance as, if this is the rotor circuit, and the external resistance you need to add up how much? 0.27 ohms per phase of star connection. R phase, Y phase and B phase, like this. So this is the rotor, by the way. This is the rotor and this is extra resistance. And of course, if you have the stator also, the stator is of star connected. Stator is also star connected. I am not writing, this is only winding. I am not writing resistance nature. So this stator is given to 3-phase supply. We have an air gap between stator and rotor. Okay. So 0.277 ohms per phase is the answer. Now if you look at this one, a 5 kilowatts 220 volts DC shunt motor has 0.5 ohms armature resistance including brushes. The motor draws a no load current of 3 amperes. The field current is constant at 1 ampere. Assuming the core and rotational losses are constant and independent of the load, the current drawn by the motor while delivering the rated load for the best possible efficiency. So this is under no load condition. He has mentioned 3 amperes, 1 ampere, like this. From no load you will get no load losses. Okay. From no load you will get no load losses. And he is asking during load condition. So that is rated load condition. Rated load condition. So while the rated load is connected, for the best possible efficiency, he is asking the current drawn by the motor. In this case, the current drawn by the motor is how much? Okay. So if it is driving rated load, means it is going to develop rated power. No? Rated power it will be developed. Rated output power it will develop. Rated power output it will develop. How much I can take up the mechanical power? I can take up it as EB into IA. Okay. What is EB? The back EMF in this case, back EMF will be 220 volts supply voltage minus drop. Supply voltage minus drop. 220 minus drop is IA into 0.5. We do not know what is the current drawn by the motor. So if you multiply this, it will be 220 IA minus IA square into 0.5. Now you need to check rated power output. What will be the rated power output? Did he mention anything about in HP? No, he did not mention. Generally, If the nameplate details are mentioned in HP, this is output power. Kilowatts, if it is given, then generally we take up it as input power. Okay, input power. So how do you take up then? He did not mention output power. So what we do is we take up the information of input and we add up, we subtract losses here. Okay, input minus losses is going to be the output now. Input minus losses is going to be the output. But if we do like that, input minus losses, rated output. So rated input minus losses. You can take up rated input minus losses. If you do like this, according to IAC key, it is not matching. What they assumed is, they assumed this 5 kilowatts as output power. Actually, it should not be output power because 5 kilowatts is the input power supplied to the motor. Generally, output is represented in terms of HP, horsepower. Input is represented. Motor input is what? Electrical energy. We represent like that. Generator output is electrical energy. We represent like that. Right. So here they have taken, instead of um, input minus losses, they considered the input as output only. They consider the input as output only. So please, uh, take this point as the rated output is 5000 or 5 kilowatts or 5000. Along with this one, actually the power which is produced at this armature, the power produced at the armature is how much? Total power supply minus armature losses and this shunt field copper losses. Okay, that is what you need to take up. Total power supplied to the motor, total power developed at the armature is taken as total power supplied minus armature losses minus shunt field copper losses. That can be taken. From the no load information. Total power supplied is what? Total power supplied to the motor. 220 into 3, we'll get 660 watts. This is the total power supplied to the motor. Out of this, how much is the shunt field copper loss? Shunt winding losses is nothing but constant loss. That is, we have 220 volts. 220 volts into 1 ampere. We'll get 220 watts is the shunt field winding copper losses. Remaining, what is the loss? Ia square. So we know 3 amperes is entering and 1 ampere is leaving. Remaining current Ia is going to be 3 minus 1, 2 amperes. So you can get armature copper losses also. 2 square into 0.5. 2 square into 0.5, 1 by, so this is 4. 4 into 0.5 is 2. 2 watts. So if I subtract these, then I can say that the remaining power is nothing but the remaining power which is developed at this armature, which is going to be supplied as no load losses. Because total no load losses, this is the no load loss, na? This is the total load no loss. No load losses consists constant losses plus variable losses. We got constant loss as core plus mechanical plus shunt field copper losses, and variable losses are Ia square into Ra. Okay. No load losses we got it as 660. Core plus mechanical we do not know. Plus shunt field copper losses as 220 plus armature copper loss as 2. So if I subtract this, then I'll get core plus mechanical losses. We also call it as core plus mechanical losses. Core plus mechanical losses generally rotational losses. So core plus mechanical losses will be equal to 660 minus 222. So 224, 40, 438 watts. So this core plus mechanical losses will be always there, whether it is under no load, whether it is under half load, whether it is under full load. So while developing rated power also, this loss will be there, 438 watts. Okay. So this is the total power developed. Total power developed is not just 5000. 5000 plus 438. Actually, we have to take it as 5000 minus 438. 5000 minus 438. But if you take 5000 minus 438, it is not matching to the answer at all. Okay. And the losses here, you need to consider all the losses, the shunt field copper losses, um, um, yeah, the shunt field copper losses, remaining armature copper losses. If you can subtract all these losses, you're not getting answer. So what they assumed is 5000 watts as the output power, and the output produced at this armature during rated load is equated to this value, 5000 plus the constant losses. Because while rotating at rated load also these losses will happen. No? This much of power you need to supply, right? Will be there. So 5438. So if you solve this one, it will be 0.5 into Ia square minus 220 Ia plus 5438 is equal to 0. So if you solve this quadratic equation, Ia1, very, very large value you will get, and Ia2, small value you will get. Okay. So he's asking the current drawn by the load, rated load, for the best possible efficiency. If you want best possible efficiency, input must be less. If you want input as less, current drawn by the motor must be less. So we select armature current as the least current. So you select this one. So if you solve this quadratic equation, you will get the armature current as around 26 something, 26 point something you will get amperes. But that is not the answer. The answer is he's asking line current. So what is the line current? Line current is equals to armature current plus shunt field current. 26 plus 1, it will be around 27 point something, 02 or something, whatever approximate answer. This plus armature current plus shunt field current, that could be the answer. So please be careful. This calculation they have considered, until unless how they have taken the given power rating, you can't judge. So they have taken power rating as output power rating. If it is input power rating, 5000 minus all the losses, if you do so, it is not matching with the answer. And once again I'm repeating, the power developed at the armature is must be equated with this term. The power developed at the armature must be equated at this term. 5000 plus along with the core and rotational losses. Then it is matching. Otherwise it is leading to conflict. Okay, so these are some questions from electrical machines. So